So this is chapter 14.3, the last part in chapter 14, behavior of gases. In this part of the chapter, we will understand the relation between pressure, volume, and the temperature of the gas. Pressure means الضغط, volume الحجم, temperature درجة الحرارة. Uh, what will happen to the weather balloon as it rises up? If you have a balloon and you fill it with helium, like this one, like this balloon, that's called weather balloon. They attach some devices like pressure gauges, like pollution measurements, and some stuff to this balloon, and then they will leave it to rise up. So they will measure these variables in a certain time in a certain location. This weather balloon usually is filled with some gases like helium. And because it has a lower density, so it will move up, like exactly like the floating. Okay. When it moves up, it goes to the upper layers of the atmosphere. In the upper layers, as we said before, the pressure decreases. Okay, the pressure will decrease as this weather balloon moves up. So what's happening actually is its volume will increase. So it will expand more and more as it rises up, okay, until at a certain height or a certain altitude, the balloon itself will pop, okay, it's like will explode or something like that, and then the devices will return back to the ground. The point here is what? There is a relation between pressure and volume. When the pressure goes down, the volume will increase. Here in this piston, for example, if we push the piston down with a certain force and this force increases, okay, so the pressure will increase, okay, so we can notice that the volume of the piston, المكبس, will decrease. So there is a relation between pressure and volume. Here also in this chamber, this glass chamber, it's called the vacuum chamber, we put a balloon inside. And then we will suck the air using a vacuum pump. We will suck the air from this chamber. So when we suck the air, the pressure will decrease. Okay? So what happened to the volume of this balloon? The volume of the balloon will increase. The volume of the balloon directly will increase. So there is a direct relation between volume and pressure. What is it? At a constant temperature, when the temperature is constant. Okay, and you can keep the temperature constant by attaching the piston body to a big object like a certain metal table at a constant temperature. So this will maintain the temperature of the piston to become constant. And then you will push the piston with a force and try to increase this force. So by increasing the force, the pressure will increase. Why? Because pressure equals what? You remember? Force over area. That's right.
Area.
Force over area. Area of what? Area of the piston. Usually, most of the pistons, or I would say, I don't want to say all of them, but according to my knowledge, the pistons are circular. Usually, they are circular. Okay, so their area is pi r square. You know that? The area of a circle is pi r square. So if you divide the force, this force F, over area, this gives you the pressure. So the area is constant. Area does not change. But the force, if you increase the force, the pressure will increase. And that's what we need. Okay, so you will increase your force, so the pressure will increase. What will happen to the volume? The volume will decrease. The volume will decrease. And you can see it if you record some points between volume and pressure. We can see that when the pressure increases, the volume will decrease, and vice versa. If the pressure decreases, the volume will increase. So the relation between pressure and volume here is an inverse relation. Inverse relation. P is inversely proportional to volume. Pressure is inversely proportional to volume. If the pressure increases, the volume decreases. So we say mathematically that pressure equals a constant divided by volume. Constant divided by volume. This is proportionality. So take the volume to the other side, it goes to the numerator. So I can say that P times V equals to this constant. What does it mean P times V is constant? At any time, at any point on this curve, if you take any point, take the volume and take the pressure, volume and pressure, volume and pressure, volume and pressure, volume and pressure, at any point. Okay? And if you multiply this pressure times this volume, it gives you the same number. The same number. That's what we call Boyle's law. So what we have just said is called Boyle's law. This law states what? That if you have a fixed amount of gas, if you have some gas and you put this gas in a piston or in a balloon or whatever container, as long as it's a constant amount of gas or a fixed amount of gas, and also you have to keep it at constant temperature. So don't put it in fire, don't put it in the fridge. You have to maintain the temperature constant. What will happen? Pressure and volume are inversely related. So V is inversely proportional to P, or we can say V times P is constant, or PV at any point equals PV at another point. Okay? So if we take this piston as an example, at the beginning I will apply a force F1. So this will give you a pressure P1. This pressure, let's say it's 100 kilopascal. And the volume of the gas, let's say the volume of the gas in the piston is 10 liters. So that's V1. So record P1 and V1, which gives you this point. Then go to try to increase the force. I will increase the force, so I will increase the pressure. Let's say the pressure becomes 200 kilopascal. So I will notice that the volume will decrease normally. So let's say the volume V2 is 5 liters. So I will record another point. Then I will do the same, increase the force F3. So the pressure will increase P3, so the volume will decrease V3, and I will take a third point. At any point, P times V is constant. Try it. P times V is constant. If you take many points, okay, they will act, or they will represent this curve that P is inversely proportional to V. Okay? This curve, actually, this curve is like y equals 1 over x. You know that? Y equals 1 over x. Or here it will be P equals something over V. It's not 1, but it's a constant over V. So it gives you this shape. This constant depends on what? Depends on what kind of gas. Depends on the temperature. What's your temperature? Okay. So for example, here in this graph, you can make or you can plot the curve at different temperatures. So at each temperature, but you have to maintain the temperature constant. So if you will do this experiment, you have to maintain the temperature constant. So let's say you will do it at 1000 Kelvin, or at 500 Kelvin, or at 273 Kelvin, which is the room temperature, or a very low temperature like 100 Kelvin, or so on. So each one gives you a curve, but all of these curves are constants over volume. But the constant is different. The constant of the first curve is different from the second curve, is different from the other curve, because the constant depends on the temperature. Also, it depends on what kind of gas. So let's say if you have air, it will give you, for example, this curve. If you have helium or nitrogen or other gas, it will give you different curve. But it has the same behavior. When the pressure increases, the volume will decrease and vice versa. The second part is the relation between volume and temperature. Let's say you will fill some balloon with air. You will buy a balloon from the market and then you will blow air in this balloon and tighten the balloon. And usually you do that in the normal temperature, in the room temperature, which is usually around 25 degrees Celsius. Okay. Let's say you will take this balloon and put it in some hot water, like boiling water at 100 degrees Celsius. So you increase the temperature. Did you increase the pressure? No, because our pressure is the pressure around us. That's the atmospheric pressure. And by the way, in a balloon, the pressure inside equals the pressure outside for the balloons. Okay? Because it's very thin membrane and elastic membrane. So the pressure inside the balloon equals the pressure outside the balloon. So as long as we have the same pressure, which is atmospheric pressure, so I expect the pressure to be constant. So I have increased the temperature. So this balloon, this small balloon, will expand. Its volume will increase. And if we take the same balloon and put it in some ice water at 0 degrees Celsius, we will find that when we decrease the temperature, the volume of the balloon will decrease. Okay? If we make a relation between, let's say, volume and temperature. At 0 degrees Celsius, let's take at 0 degrees Celsius, we will take a point here. And then at, let's say, 25 degrees Celsius, I will take another point here. And let's say at 100 degrees Celsius, I will take another point. We will find that if we take many points, they will lie on a straight line. They will lie on a straight line. So the relation between volume and temperature is they are directly proportional to each other. Okay, and the relation is very simple linear relation. Okay. So if we look here, I will heat up a certain piston. So this is the volume of the piston. I will keep the pressure constant of the piston by putting, let's say, a constant mass on the piston. So this will keep the force constant because it's constant weight. And as you know, pressure is force over area. The force is constant, the area is constant, so the pressure will maintain constant. So now I will play with temperature and I will record the corresponding volume. If you heat up the piston, the temperature of the gas increases and the volume will increase. So you can see that when this one increases, the other one increases. Of course, if you make this experiment at different pressures, it will give you different relations. Okay, but all of them are straight lines. Okay, so volume here is directly proportional to the temperature. So I can say that the volume equals a certain constant times temperature. Take the temperature to the other side. So I will say the volume over temperature equals to a constant. Okay. What does it mean volume over temperature is constant? That if you take any point on the curve, any point, take this point, take this point, this point, measure or record the temperature and the corresponding volume. If you divide volume over temperature at any time, it gives you a constant. Okay? And they are represented by a straight line. This constant depends on what? As you see here, the constant depends on the pressure. If you do it at let's say the atmospheric pressure or double the pressure or 4 times the pressure and so on. Okay. That's what we call actually Charles' law. Charles' law. So Charles, he was working with Boyle actually Okay, and I think he was a student or a graduate student for Boyles for some time, and he did some experiments with him. This is one of the experiments that he did the relation, or he found the relation between volume and temperature at constant pressure. So Charles' law states that at a fixed amount of gas, you trap some gas inside a balloon or inside a piston, and you have to maintain the pressure constant. You will do this experiment at a constant pressure. So what will happen? The volume and temperature are directly proportional to each other. They are directly related. So V is proportional to T, or V over T is a constant. So I would say V1 over T1 equals V2 over T2. The most important thing here is what? And this is the big mistake that most of you make in the exam. Temperature must be in Kelvin, not Celsius. Not Celsius. So when you substitute in this equation, you have to change the Celsius into Kelvin. How to do that? It's a simple relation. Kelvin, the temperature in Kelvin, equals the temperature in degrees Celsius plus 273. Okay, guys? So the Kelvin equals Celsius plus 273. So as you see here, for different gases, also the lines are different. So this constant also depends on what kind of gas. So it depends on the pressure and also depends on what kind of gas. So Charles, he did the experiments at different temperatures, okay, for different gases. He found something very, very strange. What is it? He found that if he extends the lines, يمد الخط, if he extends those lines, they will meet in one point, the same point. All of them, they will meet at the same point. And he found that this point, it is 0 Kelvin. All of them, they will meet at 0 Kelvin. What does it mean? It means theoretically, if you decrease the temperature, the volume will decrease. And theoretically at 0 Kelvin, the volume becomes 0. Of course, that's not gonna happen, okay, but it says at 0 Kelvin, the volume will decrease, and theoretically it becomes 0, but actually it's not, because the gas, when you lower its temperature, it will not maintain gas, or it will not stay as a gas. It will change into liquid. And sometimes, or for most of the elements, this liquid, if you decrease its temperature, it turns into solid. Okay, so it's not gonna stay in gaseous state. Okay, so the 0 Kelvin here is what we call the absolute zero. We call it the absolute zero. If you extend all of these lines, they will meet in the absolute zero. What is the absolute zero? It's the 0 Kelvin temperature, which is in Celsius equals what? Negative 273. It should be 0.15. Should be 0.15 Celsius. This is the exact number. At this theoretical temperature, what will happen? The particles of the matter would come to a complete stop. They will not move anymore. Why? Because temperature is what? We said temperature is the average kinetic energy. This is the average kinetic energy. And if you reach to 0 Kelvin, that means 0 kinetic energy. So we expect that, and actually this is true actually. If we reach to the 0 Kelvin, the particles, the molecules or the atoms, they will stop vibrating, they will stop movement. So they will behave as one big atom. They will behave as one object, one big object or one big atom at the 0 Kelvin. And actually scientists, they were able I think in 2014 to cool down like one big, like it was like 1 cubic meter of copper, I think. They were able to cool it down until they were able to reach 0.1 Kelvin. They were very near to the 0 Kelvin. And that's 1 cubic meter of copper, very big amount of copper. On a small scale, many labs, they are able to reach maybe 0.00000001 Kelvin. I think the lowest, according to my knowledge, it's 100 nano Kelvin. Nano Kelvin. Okay, that's a very small number. Okay, but this is for very small amount of material. But for big material, I think they were able to reach to 0.01 Kelvin, which is very, very near to the 0 Kelvin. Okay. Let's try to solve some problems together. To what Celsius temperature? So he's asking about what Celsius temperature must a gas sample that is initially at negative 20 degrees Celsius. So this is the temperature T1, and he's asking about a temperature T2 or T final. A gas that is at initially at negative 20 degrees Celsius be heated if the volume is to double at or its pressure remains the same. So here I have a constant pressure. And there is a relation between temperature and volume. So that's Charles' law. V1 over T1 equals V2 over T2. So here he says what? What is the second temperature? What is this temperature? If I start by negative 20 degrees Celsius and I need the volume to double. Volume to double means what? The second volume equals double the first volume. 2 times V1. Okay. So I can remove this V1 with this V1. So the relation becomes what? 1 over T1 equals 2 over T2. What is the temperature T2 if the temperature T1 is negative 20 degrees Celsius? So I will write here negative 20. Is it right? No. That's a big mistake. That's a big mistake to substitute the temperature in Celsius. I have to change it into Kelvin. Okay? We need to change it into Kelvin, so it's plus 273. So 1 over 253 equals 2 over T2. Okay, guys?
دكتور
Yes?
هل في مشكلة لو عوضت بالسيليسيوس بعدين النتيجة جبتها
Yes,
في كالفن؟
it will be a big mistake. I will tell you why. If you have a ratio like this one, 2 over 3, and I have a ratio like, let's say, 2 plus 5 over 3 plus 5, are they the same? Is it the same ratio?
No, of course.
It's not the same ratio. So if you add something, if you add a number to the numerator and denominator, it gives you different ratio. Okay? So if you add 273 here, it's not the same as if you leave it as it is. Okay? So you have to change it first.
Okay, thanks.
Okay. So the temperature T2, I will find it. It becomes 506 Kelvin. So this is the result. But wait, he's asking about what? Celsius temperature. So he wants the output to be Celsius. So I have to change it back into Celsius. 506 minus 273. The result will be 233 degrees Celsius. So this is the result. Okay, guys? Let's see something else. A weather balloon. A weather balloon has a volume liter or litre. Litre is French, liter is English. 1 cubic meter, for example, 1 cubic meter equals 1,000 liter or litre. Okay? 1 cubic meter, this is the SI unit. The 1 cubic meter or the cubic meter equals 1,000 liter or litre. Okay? Weather balloon has a volume of 90 liter when it is released from the sea level, where the pressure was 101 kilopascal, 1,000 Pascal. find what is the atmospheric pressure. So let's say that's P1, and he's asking about P2 on the balloon when it's grown to a size 200 liters. So this is a volume V1 and this is a volume V2. Assume temperature is constant. So that's what? Boils. So P1 V1 equals P2 times V2. In Boyle's law, you can use the SI units or other units, as long as the units on the two sides are the same, so you can use whatever units you want. Okay, so you can use the pressure in Pascal or bar or atmospheric, doesn't matter. The ATM doesn't matter. And volume, you can use it in cubic meter or liter, doesn't matter also. So P1 is 101 times V1 is 90 liter equals P2, this is what I'm searching for, times V2 is 200 liter. So I use the liters on both sides. And I use the pressure in kilopascal. So the pressure P2, it will be found in kilopascal also. So the P2 is 45.5 kilopascal. Okay, kilopascal. The third one, a balloon is launched at the sea level, where the atmospheric pressure is nearly equal to 100 kilopascal. So that's the pressure P1. Density of the hot air chamber of the balloon is 1 kilogram per cubic meter. So this is density, الكثافة, density. Usually we call it rho. What is the density of the air inside the chamber? So let's say the first one is rho 1. So he's asking about rho 2. Inside the chamber, when what? When the balloon has risen to a height where the atmospheric pressure is 33 kilopascal. So this is pressure P2. And he needs to say that the temperature is constant. At a constant, or consider the temperature constant. So I will use what? P1 V1, Boyle's law, equals P2 times V2. Here I have P1 is 100 kilopascal. And P2 is 33 kilopascal. So there is a relation here between the volume V1 and the volume V2, but I don't know anything about the volume. He just gave me the what? The density, and he asks for the density. Density rho 1 and rho 2. Is there a relation between volume and density? Yes. You remember this equation? Mass equals density times volume. Mass equals density times volume. Or density, you can say density equals mass over volume. Or you can say also volume equals mass over density. All of them are the same. The three relations, they are the same, but different forms. So I will use this one. Volume equals mass over density. I will substitute it here, and let's see the relation looks like what? 100 times. V1 is the mass at the beginning over the density at the beginning, equals 33 times. The volume V2 is the mass at the end divided by the density at the end. But this is a balloon. He should say actually it's a weather balloon. In this balloon, there is a fixed amount of gas. Fixed amount of gas. So the two masses here are the same because it's the same amount of gas. Okay? So the mass M1 equals the mass M2, so I can remove M1 with M2 because it's the same amount. Yes.
ليش طيب ما عوضنا ال V1 بواحد كيلو جرام؟
Because the 1 kilogram per cubic meter, it's not the volume. This is the density, الكثافة. Okay? So I don't know what is the volume actually. I don't know the volume. Because to know the volume, you need the mass. And I don't know what is the mass. Okay? So it becomes like 100 over density 1. Excuse me. What is it? Equals 33 divided by density 2. Density 1 is what? Is 1. So I can find density 2, rho 2 equals 33 times 1 over 100. That's 0.33 kilogram over cubic meter. Okay, guys? So this is the density. Let's try to solve this one. This is about buoyancy.
Yes.
Yes.
What does fixed mean?
Fixed means constant. It's a constant.
Okay.
Okay?
Thank
Does not change. So here I have a rectangular box, like a piece of wood or ice. It has dimensions 7.6 times 3 times 3.7. In this problem, guys, I will need you to have a calculator so you can calculate with me. It weighs 350,000 Newton. So the weight of this box is 350,000. So now you know the volume. This is the dimensions. So you can calculate the volume of the box, of the block, or the block. The volume of the box equals what? 7.6 times 3 times 3.7. So if you want to find the density, you can find it. Okay, you can find it if you want. Okay. And is floating in fresh water, as in the figure below. How deep, عمق, the submerged part, الجزء المغمور, of the box. How deep is the submerged part of the box? So part of the box here actually is submerged inside the water. So I need to know what is the height, how deep this part in the water. For the floating object, we said before that this object is balanced under two forces. What are these forces? The weight of the object, the weight of the box, and the buoyant force. So I can say that the buoyant force equals the weight of the box. What's the buoyant force? Buoyant force equals what? Equals rho times V times G. You remember this equation? Rho, the density of what? Density of the box or density of the liquid, of the water? Density of water. Remember that the buoyant force, density of the liquid or the fluid. Volume of what? Do you remember what is the volume? Volume of what, guys? Volume of the object or volume of what? Huh? Do you remember?
Of
The
object.
submerged part.
The submerged part. Excellent. This is the submerged part times G. So I will equate now the buoyant force to the weight of the object. So I will say the weight is 350,000 Newton equals the buoyant force is rho. Rho here he gave it to me. The density of water is 1,000 kilogram per cubic meter. So 1,000 times the volume of the submerged part. This volume, what is it? I don't know. I will call it V sub. Times G, it's 9.8. So from here I can find the volume of the submerged part. Please do it and find the answer, guys. What's the volume of the submerged part? If you have a calculator, please try to do it.
35.
35.
35.7.
171.
0.71 cubic meter, right? The result in cubic meter, because here I have standard units. Okay, But I'm not. He didn't ask about the submerged volume. He asks about what? How deep? I need the height. I need the height. The height h. How to get it? What do you think, guys? This submerged part has the shape of what?
rectangle.
So it's like a cuboid. Okay. So its volume is what? The volume of the submerged part is what? Is width, this width, which is 7.6, or this length actually, I would call it the length, this is a long one, times width. This width is what? 3. Times height, I don't know the height, but I will call it h. So I will equate the submerged volume, which I found at 35.71, to what? To the 7.6 times 3 times h. I will make this equation, so I will find h to be what? Can you get it?
1.5.
1.56.
1.566 meters. So this is the height, 1.566 meters. Okay, guys? So in this kind of question, he might ask what? He sometimes asks, what is the volume of submerged part? Okay, so I get it here, 35. What if he asks you, what is the volume of the part outside the water, the other part? What will you do? If he's asking what is the volume outside the water?
طرح الجزء المغمور من الكلي.
That's right. The total volume is here. This is the total volume. Where is it? Total volume is here. V bucks 7.6 times 3 times 3.7. This is the total volume minus the volume that you get, which is the submerged, gives you the other part. He might ask you, what is the height? What is the height of the part outside the water? H. Or let's call it D, for example. D. You will do what?
We will 3.7 minus 1.56.
You have two methods here. You can say 3.7, which is the total height, minus the height h that you get. So we can say 3.7 minus 1.566. It gives you the other distance d. That's a method. The other method is what? You can get the volume of the part outside the water. The volume outside. And then you can say the volume outside equals what? The same issue like what we did here. We can say the volume outside equals length, which is 7.6, times width, which is 3 meters, times height, which is d. And then you can find d, it will give you the same number. Okay? So you are flexible in the method that you will use in such problems. A beaker that is completely filled with water. I have a beaker here that's filled with water to the top. To the top. So if you put anything inside, it will overflow. Water will overflow and spill down. Okay? So a beaker that is completely filled with water weighs 30 Newton. So it weighs 30 Newton. As in the figure below. What would be the reading of this scale? I need to find the reading of the scale when 5 Newton block of wood floats in it. If you put a 5 Newton block inside the water, what will happen? Do you think it becomes 35 Newton?
No.
No,
Course
I think
not.
it will be the same.
It's the same.
Because you will lose some water. When you put this block, you will lose some water. Okay. What is the weight of this water? That's called, if you
5
remember,
Newton.
the weight of
5 Newton.
displaced water, الماء المزاح. And we said this is equal to the buoyant force. If you remember, the definition of buoyant force equals what? The buoyant force equals the weight of the displaced water or the weight of the displaced liquid or fluid. Okay? So you will lose some water. Its weight equals to the buoyant force. What's the relation between the buoyant force and the 5 Newton?
They are equal.
They are equal. Why? Because it floats. When it floats, it's affected by two forces. Its weight downward, which is the 5 Newton, and the buoyant force upward. And they are balanced. So the buoyant force equals to the weight of the object. So the buoyant force equals to 5 Newton. So the weight of the displaced water equals to 5 Newton. It means you lost 5 Newton when you put the 5 Newton block inside the water. You added 5 Newton, but also you lost 5 Newton. So this will maintain the whole weight constant. So the weight stays 30 Newton. Okay, guys? So that's everything in this lecture. I hope you enjoy it. And please, if you have a question, please ask me.